The modern web browser functions as a high-speed execution engine, an application runtime environment processing thousands of operations per second to maintain complex software. To understand these systems, we reference the framework in the Royal Research Technical Guide. This provides a system-level blueprint for analyzing web interfaces. Early web development involved servers distributing static pages. Today, engineers build state-driven software that executes directly on the user's device. This shift introduced a massive engineering challenge: managing escalating user interface complexity. Without strict organization, a modern web application rapidly becomes impossible to maintain as the codebase expands. To use tools like React effectively, you must first deconstruct the fundamental mechanics they manage: component-based design, single-page applications, and state management. Approaching the modern front-end as a purely visual discipline neglects the structural complexity of the browser, necessitating a move toward rigorous software architecture. We start at the historical baseline established by Royal Research. This diagram shows the original architecture of the web. A server pushes a single pre-compiled block of HTML down a one-way pipeline to the browser. This model operates with a functional limitation. Once the HTML arrives on the client device, it is fixed. There is zero client-side interactivity, and the data cannot change. The first structural evolution introduced server-side scripting languages like PHP and JSP. Now, before sending the file, the server connects to a database, extracts custom data, and compiles a dynamic HTML document. But look at the lifecycle of a user interaction here. A user clicks a link, the browser sends a request across the network, the server processes the database query, compiles a brand new file, and sends it back. The flaw in this cycle is the user experience. Every single click requires a complete, inefficient wipe and reload of the entire visible interface. Relying on a distant server to compute and redraw the user interface for every minor interaction bottlenecks the application's responsiveness and limits scalability. To bypass the server reload cycle, engineers turned to JavaScript. It allowed them to execute logic directly within the client's browser. This diagram illustrates the document object model, or DOM. It's a hierarchical tree representing every visible node on a web page. Early JavaScript delivered interactivity by directly targeting specific nodes on this tree and manually altering their state based on user input. This worked for simple pages, but as applications scaled, tracking manual changes across thousands of connected DOM nodes became exponentially complex. Direct manipulation often leads to spaghetti code. When independent scripts constantly overwrite each other's changes, the application becomes brittle and difficult to debug. JavaScript solved the server reload bottleneck, but by manipulating the DOM directly, it triggered a massive client-side logic crisis. The structural solution for tangled DOM logic is component-based architecture. A component is an encapsulated, reusable unit. It contains its own HTML structure, CSS styling, and JavaScript logic, entirely isolated from the rest of the application. Modern web apps assemble these isolated components into a predictable, nested hierarchy. This structure is the foundation of the single-page application, or SPA. In an SPA, the browser loads a static HTML shell exactly once. As the user interacts, the application simply swaps out internal components dynamically without reloading the page. Because the UI files are already on the device, the front-end communicates with the server exclusively by fetching raw data via APIs. Engineers route this raw data into the front-end using methodologies like RESTful APIs or GraphQL, querying only the precise datasets required. By utilizing SPAs and component models, developers successfully separated the data layer from the presentation layer, allowing the front end to function as an independent system. This decoupled architecture requires a central nervous system, known as state management. This animation shows how centralized state tools, like Redux or the Context API, solve the decoupling problem. They synchronize incoming data and push updates across disconnected branches of the application simultaneously. Managing all of this requires a highly strict infrastructure. Build tools compile these modular files and optimize the final assets so browsers can actually read them. And because the front end now houses immense logic, automated testing frameworks like Jest are mandatory to verify the integrity of the code. Rigorous architecture also builds non-functional requirements directly into the components. Engineers apply responsive design to adapt the layout to any screen, alongside semantic HTML. Utilizing precise area roles and semantic structure ensures these JavaScript-heavy interfaces remain accessible and usable by assistive technologies. Equipped with centralized state, automated compilers, and testing frameworks, the front end operates as a complete, standalone software ecosystem. Libraries like React are simply prepackaged, highly optimized implementations of the exact architecture we just constructed. React's specific answer to the speed limitations of manual DOM manipulation is a concept called the virtual DOM. React creates an in-memory copy of the UI. When data changes, it calculates the differences in the background, isolates the exact nodes, and updates only precise spots on the real DOM. This abstraction removes the burden of tracking manual DOM nodes from the developer. Using the decision matrix from the Royal Research Technical Guide, engineers deploy React specifically when a project requires complex state management, heavy integration with third-party APIs, and highly interactive components. However, applying React to a largely static content site is a severe architectural mismatch. It introduces unnecessary execution overhead for zero operational gain. Specific frameworks and libraries will inevitably rise and fall, but mastering the core underlying principles of component isolation, API routing, and state management ensures your architecture remains scalable and resilient.